When you're sketching graphs of derivatives, you need to keep in mind that you're graphing the slope. You're graphing the slope of something, not necessarily trying to follow the original function itself. Let me clarify. Okay, the slope of this piece is positive. And I know that this section right here is a line. So I'm going to just, anywhere, I'm not going to be too picky about where. Let's put a horizontal line that corresponds to this. The slope of this piece is negative. It is a constant negative. This is a constant positive. Why are these open circles? I'm glad you asked. They're open circles because at that point there is no slope. It's hard to determine, it's impossible to determine the slope of a point at the peak. Positive slope, negative slope. But what's the slope right there at that particular point? Well, it's somewhere in the middle. It's not zero. That would be zero if it was rounded, which leads us to the next one. Boy, I wish this thing would align correctly. That'd make my day. We'd have a party in here. I tried to scroll without writing on there. Pull out a big sombrero and start dancing around the room. It'd be great. Okay, everywhere where you have a maximum or a minimum, and it's not an absolute value, in this case particularly, you're going to have a corresponding x-intercept. There's one. Because the slope is zero at that point. It ceases to be increasing and becomes decreasing. Notice I just said increasing. This is increasing. Don't let this fool you that because this is increasing, then the graph of your derivative is going to go up. It's not. Because it's increasing, the graph of your derivative is going to be above the x-axis. And it better touch that point. So it better go down. That makes no sense. It makes perfect sense when you think about it in terms of slope. From here to here, it's decreasing. So it's below. From here up, it's increasing. So it is above. I want to point out one other thing. When dealing with the second derivative,